Okay, today I'm going to show how keyboard scrap can be used to develop a function that calculates a Fibonacci series. Fibonacci series is a series of numbers where the next number is the two previous numbers added together. So it would be, and so on. So pretty simple function, we've all done it before, but I'm going to demonstrate how to develop it without knowing much, and also a couple of different implementations using keyboard scrap. This is my keyboard scrap playground. It's got a keyboard scrap ID. It imports KS, which is the Swift file that I've developed to support keyboard scrap functionality in my playgrounds. I'll do a video about that at some point, but essentially we get these play functions and our keyboard scrap function, and we put our tests in between them. So it works like this. We want to keep, if everything works, keep with throw, so that then we play that, because we can see here we've had a test pass, we've kept all the changes. If we put false in there, that we can't, this fails, so it'll revert, scrap that and change it back to true. And this is the essence of keyboard scrap. So for Fibonacci, we have function takes an integer, it outputs another integer, and the first number it outputs is a 0, so we're going to keep that. Obviously that's kept because we're just checking if it's true, you know, we're keeping if true is true, and true is by definition true. So we need to test for our function 0, 0. So basically that's the first test against our function. Again, successful because this is 0 and we've hard coded it. The same goes for 1. So let's go to test first now. We want to return, if we look for a 1, we want to return a 1, so we can just return n, and that will pass. And you see we're anywhere near a correct function here, but we've got two. It's like a clock is always right, a stopped clock is always right twice. Well, this function is always right just twice, because the next thing we try should be 2. It's going to fail, and it's failed pretty hard, so it deleted the test that made it fail. And we need to start writing some code that's going to pass the test. So we're happy with that simple case, but if n is not less than 2, i.e. 2 and above, we need to do something fancier. And of course it's adding the two previous numbers in the sequence, so it's actually pretty simple because it's Fibonacci. Return fib n minus 2 plus fib n minus 1. Just get that call in right, and we want to test. Let's keep this. Now if we don't test that particular piece of code, then it's going to pass, but let's make a test now. We expect that to be 1. It's 1. We expect it the next one to be 2. and the next one to be y. No, yeah, 4. Oh, we didn't get that right. Right, let's think hard about that. 0, 1, 2, 3, 4. Oh. Yes, it's 3. So I'm getting ahead of myself. And this is it, you know. Basically, if you get a test wrong, it's just as bad as getting a piece of code wrong and it deletes it for you, so you don't have to worry about bad tests lasting not too long. So we're getting there. I think we'll just test the last one and so on. Now we're fairly confident that that Fibonacci function is correct and working. However, it's not the most efficient function in the world because it calls itself recursively. In fact, it calls itself recursively 2 recursive calls per call, which makes it exponentially bad. So what can we do to improve this? Well, let's write a second Fibonacci. But we're going to do and try to make it a bit. In fact, let's call this, and we're going to do the same. Can't really get better than that. So basically, it's what can we do here? Let's put some tests in. So this is our second function. Right, I think that will compile. Yeah, so again, we've got 3 in the series correct, but that's because we've hard coded anything after the second one to be 1, and of course we know that if we try to go for that, make that one, third one is 2, then we're going to fail because this doesn't return 2 ever. But what we can notice is, yes, it's a series, so each of the first 2, which kind of seed the series, then you just add the previous 2 to get the next one. So 1 plus 0 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 8 plus 5 is 13, and so on. So that's what we need to get here, is we need to set up some variables. Let's call them A equals, this is our seed, so this is the first 2, and we want to return them added together, but we want to kind of step through the series. So what we want to do is count through from 2 to n, and we want to do this. We want to step through. So I'm going to save a into a temporary variable, temp a. We're going to make b, no, we're going to make a equal b, so that's moving up, and then we're going to add the 2 previous ones. So b is going to be, no, yeah, that's what we, sorry, that's what we want, but we can't get that because then that will ruin, we can't set a before adding it in, so that's why we have to have the temp thing here, and it's going to be B, and then we're going to set A equals temp. So basically we're remembering what B is, because we're going to make that A into B, and then we're creating the addition there, and then when we've counted enough we will return. There you go. That worked. So again, let's test this Fibonacci 2. This one. And so on. So that's two different ways of doing a Fibonacci. There is a third way, potentially, because obviously we've got 3 assignments here, and we've got an additional addition there. Well, that's okay. I don't know if we can get away with not having, basically we'd be creating this temp variable, but maybe we could swap A and B around, then B would be in the right place because it would be where A was, and then we could just add it to A in A's new place. So I'll show you what I mean. Call it fib3. What I'm saying is I could swap them around. Then I can swap them around. So now A is now what used to be B. So B, we need to add A. And we can change all those, cross our fingers, and there you go. So 3 ways to do a Fibonacci using keep or scrape. First way was the naive recursive way that we all learn in computer science. Then we learn how to do an optimized one, which doesn't have the recursive calls and uses a for loop instead to loop through it. And then the third one, I have no idea whether that's better or not. It probably depends on the architecture more than anything else, on the compiler. But it's less lines of code, so if you like less lines of code, it might work. You can, use that as a measure if you like. But there you go, all created using keep or scrap.